Ми вже почали трансляцію. Hello everyone, welcome to the Postgres Lviv user group meetup number 6. It's been 2 years from the last our event. We are glad to see you all here, and also we are glad to have all who are joining us online. In addition, I want to tell words of gratitude to our sponsors, SoftServe, Everymatrix, and CyberTech.
Okay, so a couple of words about our agenda. So we are starting with the introduction and then some news about what happened in our community. Not much, really. We had a pandemic, you know. Then the first session by Hans-Jürgen Schönig. Then 15 minutes for coffee, beer, something. Second session by Ansasma. And then lightning talks. If you want to talk about, something very interesting for 5 minutes, if you want to share some views or share some ideas about projects, please. And then we'll have a raffle and after party.
We want to remind you that we have a great channel to communicate with our community. We have created a Telegram chat where everyone can ask any question related to Postgres, and our community experts will provide you with the answer in few minutes.
For free.
For free, yes. And I highly recommend you to join this channel, and you will be first whom we will notify about our news and next events.
Okay. If you are on social media, and probably you are, please share the news about our event. We use hashtag plug, you know. Means PostgreSQL Lviv user group. So please do it in Twitter or Facebook or what else we have.
Yes, and we have great gifts for this.
Okay, and then at the end of our evening, the person who will tweet most of Twitter or Facebook, or how we do it?
Facebook.
Oh, okay. We count only Facebook. So forget about any other social media. Just Facebook. Tweet a lot with this hashtag, and the person with most posts will have a present. I don't know what that, but looks like a blank something.
Yes, and if you are looking for new challenges in your life, we have a lot of opportunities from our sponsors, and please don't hesitate to contact me or Oleg Markiv from Everymatrix or Pavlo Golub from CyberTech, and we have a lot of opportunities for everyone. Yes, that's all for this part, and
yes, our first speaker, Hans-Jürgen Schönig. I know that you will introduce yourself during the talk, so
I'm disappointed.
Yes. I'm speechless.
One moment. Okay. Please. Stage is yours.
Cool, thank you. So, hello everyone. Thank you for showing up and not introducing me. Okay, my name is Hans-Jürgen Schönig. I'm running this show over there at this company, and thank you for seeing physical people after the COVID stuff. I was able to touch somebody already. It's so cool. Hello everybody to the online ones. So today I got a couple of stories, and there is some good news. I hopefully it's going to be funny, and the bad news is everything is true. So everything I'm telling you today is unfortunately very, very true. So as you noticed already, we are Postgres people, we are cool, we are everywhere. We got a couple of cool clients, but you know that already. So let's come to the cool stuff. So I prepared something today as a little bit of entertainment. Basically, just a couple of stories I collected over the past 20 years, which I mentioned already happened to be true for some nasty reason. So let me share what happens. So first thing is, I'm going to share a small story with you. So you actually visit the customer, what can go wrong? You approach some nice database problems, what can possibly go wrong? And at the end of the day, you go home, what can possibly go wrong, right? So let's see what can happen in real life if you're doing Postgres for 20 plus years. So once in a while, you get a request and they're going to tell you, can you come and help? Right? And obviously, sure, we can do that because we keep saying that Postgres worldwide, right? So we got a little request from this place here. And this is real. I didn't have no bloody idea where is that. So I Googled the whole thing. Does anybody know the country of Kiribati? Has anybody ever heard of it? Yeah, apart from you. It's the 7th largest country in the world. The highest peak is 16 meters, and the thing is gonna drown when we keep driving diesels, right? And those guys there sent us a request for a little bit of training, and I Googled this government agency. It was literally a hut on some island, which happened to be the labor agency. How would you call that? You know, those people who give you a job. And it was literally a hut on an island. So I tried to figure out how to get there. And this ship place is 6 hours west of Hawaii. It takes 3 days to get there. Seriously, in 3 days to go back. So I told them, okay, guys, don't pay for anything, right? Just pay for the flight. I'll go there, you know? The problem was we couldn't get the project because the bloody flight was 3,200 euros just to get there. And that's roughly the gross domestic product of 10 Kiribatis for a year. Something like that. So that was the first problem. So obviously, when you want to solve a database problem, you have to get there. And this is where the French did the nuclear test. So just to put it into perspective, right? So that's damn true, right? So, but obviously, if you manage to reach the client, the first challenge is to stay out of jail, right? So that's the first thing. So I remember landing somewhere, and I got out of the airplane when a nice gentleman approached me in very bad English, took my luggage, and asked me to follow. Take ground. So I literally came out of the airplane, right? And the guy called me, you know, couldn't speak English, right? And literally put me into a room, you know, alone, without my luggage, anything, right? I shit in my pants, I believe you, because this place is called Imam Khomeini International Airport. This guy led the bloody revolution in 1979, right? So they are kind of serious. What I did not know is that all they did was book the VIP launch for me when I arrived, so that they can arrange for my visa and take care of my luggage. But the problem is the guy who picked me up at the airplane didn't know any English, so he didn't tell me that this is the VIP service. It just put me in something that felt like a cell. So that was really nice. By the way, that's Tehran. It's one of the most beautiful places in the world, right? But actually getting there could already be some sort of, well, it doesn't feel right if you're picked up directly at the airplane in Tehran, right? If you don't know what for. That's not very nice. By the way, that's the old Silk Road. IT in Iran is female. So 70% of all those people they are working in IT are actually women, right? Wouldn't expect that. It's Tehran. So obviously, and forget Persian keyboards, right? So if you ever have to work on a Persian keyboard, it's like using a computer for the first time, right? So from Kiribati directly to Tehran, right, to be put in a solitary cell until somebody arranges your visa. But anyway, so let's get started with some real database work and see what can possibly go wrong there. So, what can possibly go wrong before you actually manage to connect to the database? Well, not much. There was one case, and that's the only guy who made it to my personal blacklist in 20 years. And the wording was, never call me again. Whatever happens, just don't call me again. Could he migrate the bloody database? Mr. Pavlo was working on this wonderful project, by the way, right? And sure, we can do that. So give us access to the bloody database. So there was a weekly meeting, and they said, what do you need to get started? I said, well, we need access to the database. Okay. This happened repeatedly for 6 weeks. Every week there was a status report. What did you get done? We said, nothing. We can't get there. Right? We have no login. After 6 weeks, it pissed on my shoes and said, well, we're doing this kind of call for 6 weeks and then still, you know, nothing is done and bastards, whatever. And then he figured out, well, those guys cannot get there. After 6 weeks, it dawned on him. And then the complaint was, but if we give you full access to migrate the database, you're going to see all the data. Yeah, that's the whole point. You know? This shit took 6 weeks until we finally threw him out because we cannot migrate the database if you cannot get there, right? 6 weeks just to figure out that we need access to the bloody database. You know, it just didn't dawn on them that that's necessary, right? So that's something that can actually happen. So, but finally, once in a while, some real stuff is going to happen. So once in a while, you really got a nice problem, and sometimes it's a hard one. Hans, who happens to sit somewhere here, had something very nice the other day at a company I won't name, a disk feed up, right? So disk full can happen. But how did it happen? That was the fun part. Those guys, so if the disk fee is up in Postgres, it can be really nasty. So if you ever use Postgres, make sure that the disk doesn't fill up. Postgres doesn't like that at all, right? It can have all kinds of side effects. So never run out of disk space. And it's fairly easy to prevent if you do that properly. So avoid that. But how did we get there? The problem is, how could it ever happen that the disk ran full? The customer also wanted to know. So here is the process, how it happened. There was a database, and the technician wanted to create a replica. So to do that, he checked if the target system has enough space to actually do it. He figured out that it's only 5 gigabytes too small. So they went on with the migration under the assumption that by cloning the database, it's magically going to shrink. So they actually checked if there is enough space, figured out that there isn't enough space, and did it. Can you imagine that this happens in a, well, I wanted to say civilized country, it was Germany, but never mind. So, but this really happened. They checked for free space, figured out it's not enough, and went ahead and then complained that it's not going to work, right? So that happens in German industry, hard to believe. This is also interesting. That's my favorite one. You have a database, you create a new database, And what Postgres does internally, when it creates a new database, it basically clones an existing one, right? So what Postgres does is, if you do create database, what it does is it says, okay, take all the files from this template and just copy them, right? How can you run into no such file or directory when you do create database? How can you ever do that? Does anybody have the slightest clue? How do you manage to do that?
Wrong permissions.
No. No. The solution is you start your database, drop the data directory, do a fresh init DB, and then do a create DB without restarting the server. That's how it works. The hard part is to figure out, because nobody touched anything. So that running database completely erased the data directory, completely vanished, did a fresh init DB, and then create DB failed. I think it took us a day or something to figure out that this is the case, because you wouldn't expect something like file not found to appear, because how could it happen? But the point is, if it's running, you know, it just goes away, you know, it's file not found, and you cannot backtrace that because it's obviously looking for a file that should exist, right? So this gives you file not found. That's really interesting. Who would have figured out? I guess, I mean, it takes a day. No way. I mean, like completely internal overload. How could it ever happen? File not found. That's one of my specialties. But there's even more cooler stuff. We got a request for, you know, Postgres can do similarity search, you know, trigrams, full text search, stuff like that. And there was a request coming in. They were storing the location of electric vehicle charging stations in China. And what they wanted to do is they wanted to do similarity search on Chinese characters. How do you do that? The thing is, we have no fucking clue how to do similarity search on Chinese characters, you know, because we can't even read them, you know. So this really happened, similarity search on Chinese characters. I had no clue, you know, how this could ever work, you know. Totally impossible. Does anybody know how to do similarity search on those languages? Does anybody have a clue? Because maybe we can fix that. Anybody? Nothing? Okay. Yeah, that was one of the harder parts, which are quite easy to reject, I would say. Yeah, similarity search on Chinese characters. One more. Table not found.
Another German.
Yeah, that's for some reason everything that fucks up is in Germany. So let's start from something, relation not found, but you see the table. How can it happen? You see the table in the database, you query the table, and it says relation not found. The first assumption is search path. So you try the search path, it doesn't work. You try it from the command line, and the shit does work. It only does not work from your application, but you haven't changed it. How can it happen? And the answer is, they had the Latin database. They dumped and reloaded it to a UTF-8 database, but the string in the application code is still Latin. And then it doesn't find the table anymore, because this is a Latin umlaut and this is a Unicode umlaut. So you have an unchanged application that doesn't work anymore because it doesn't find the table you can clearly see in your pgadmin. And the reason is they changed the character set from A to B, and that broke the application because the string in the application was still Latin 1. Who would have found that? Took a while. I mean, that's something you could, when you see that, you want to cry. It's like, why does it work? And the reason in this case was character set related, you know, complete fuck up. Never put umlauts into your database name. Never do that. It's like, or in the table names. This is why it failed. I mean, that was really shit thing, you know? So, next one. How do you handle complaints? So obviously you have trouble when you visit the client. Obviously you've got trouble to log in. Obviously you've got trouble, real technical trouble. So how do you handle complaints? So let's have a nice complaint here. A guy called me and asked me, can you provide high availability for Postgres? And I said, sure, we can do that. What we need is, we need 2 database servers, we need some etcd there, we need a couple of IP addresses to move them around and stuff like that, right? And then it can do automatic failovers, and it's pretty cool, and everybody loves Patroni, and that's Postgres high availability. That's really, really cool. What complaint do we have in mind? What could be a complaint a sane human would respond to this thing? The answer is, what does the second server do when there is no crash? Obviously, you have a second database server. What's the thing doing? And the answer was, well, you can use it to read, right? So you can use your database replica to actually read, or it's just going to sit and wait until something crashes, right? The complaint is, this is totally unacceptable because it was really rude. Our policy is not to buy hardware that sits idle. There must be a better way. To actually do high availability with less than 2 servers. He was really mad at me. You know, just couldn't imagine what's the point, you know? Explicitly asking for high availability, and then the complaint that actually needed a second server. So that really happens, you know, you won't believe it, but it really happens. So one more. Scanners. We sent a support request, but none of you bastards responded. Of course, we didn't get anything. And then it dawned on me. They complained about the fax machine before already. What a fax machine? So the reason was that they figured out that there was a second cyber tech in Italy that was selling office equipment. And they went bankrupt 10 years earlier. They sent us complaints that they had no drivers for the bloody scanners, the fax machines didn't work, you know, no prices for spare parts on the website, shit like that. It didn't dawn on them that this is a completely different company, and the other one is 10 years out of business. And by the way, we're selling database stuff and not office printers, right? So it completely got mad at me, and there was no drivers for Windows 98 either. That was one of my favorite complaints, right? But there's actually more. So obviously, what you can imagine if you're running a database, once in a while, it's going to be a performance thing, right? So let's talk performance. There was a guy, that was a while ago, that's really 15 years ago. They are running an important application, and the question was, can Postgres handle the load? I said, well, what's this thing doing, right? So let's talk, you know? And he gave me a specification, Oracle Enterprise Edition, 9i, whatever, right? 8 cores, 32 gigabytes of memory, which was, you know, insanity back then, you know? And it had RAID and everything, super perfect, super stuff. There was a little catch. The whole shit thing was connected to an ISDN connection, and he bought proper hardware to handle the network transfer. And then he had 6 rows in total in his entire database. 6. It was weather messages sent once per hour. So that 8-core Oracle Enterprise Edition with brand new hardware hooked up to a dial-up connection to get 6 weather messages per hour, like there's going to be a thunderstorm in Poland, it's raining in England, shit like that, just to pass it on. They basically use it as some sort of queue, right? And their concern was, can Postgres handle the load? Serious. I should have told them, we should make a study on that. I didn't, but that was true. I mean, this guy spent hundreds of thousands, on storing 6 rows about weather messages, and he was concerned about speed. Seriously concerned about speed on a dial-up ISDN connection, right? On a computer under his desk or something like that. It's hard to believe, but it's true. But there is more. There was one complaint from, I think I recently mentioned Germany. I'm not sure. Anyway, so complaint from Germany. Next one, our database is so slow. That's a common thing that happens even in Germany, right? So let's take a look. And that was the single most weird thing I've seen in my life. You have a database that is dying because of performance reason, and it checked up, query statistics, features and statements and everything, and it did not see a single where clause. Select star from A, top query. Select star from B, top query. Select star from C, top query. Always select star from table. That was all queries, select star from table. Nothing else. Why? It's tough. A where clause is business logic in the database. We do not want business logic to be in the database. This is why we keep doing select star on every table and filter on the application. What are you going to say? I mean, if you say bloody idiot, it's maybe illegal and not very nice to the customer. If you send him medical treatment, it's not good either. If you shoot him, it's illegal. So how do you handle that? What are you going to say? I mean, if there's anybody with a suggestion, maybe, but it really happened. Not a single where clause, not a single, nothing. Just select star on every table. That was it, because they did not want business logic in the database. I think you've seen this thing, right? Yeah. Completely inconceivable, right? So, but then there's also a thing related to handling results, right? So if we went to the customer, we managed to get there, we fixed all the performance problem, how should we handle results? I like this one. You have an outer join, I just made it up. You have customers, left join, turnover, and then there was a problem in the on clause, right? So there was clearly a bug in the join. And take any outer join and assume it's wrong, right? And I said, hey guys, I found the problem. This is an outer join, which means we always get the full left side and whatever matches. So the left side is always full. It's always a full set. This is not going to reduce anything, right? It's always the full left side. This is why it's slow. So it's actually not slow. It's just going to use the wrong data, right? It's just going to aggregate 100 million rows instead of 1,000 rows. It's wrong. Your query is wrong. Could be, but let's focus on performance first. I said your whole bloody application is broken. Everything you're getting out of the database is wrong. Yeah, let's fix performance first. What are you going to say, right? And he was really pissed off because he had a performance problem and I refused to help him, right? Because I told him, let's write a query that actually returns the right thing, which is going to be miraculously going to fix performance. And he was completely mad at me because I did not take his problem of performance seriously because I was pointing at irrelevant stuff such as the wrong query. This was finance. Just say. Okay? So, but sometimes it's not only, but sometimes it's a real tragedy, It's not just like, some funny problem, like, where clauses with obvious idiots or whatever, right? Sometimes it's really to be or not to be. And let me share some of the to be's or not to be stuff. Sometimes it matters, sometimes it really matters. So there was one thing, the tax office was about to seriously investigate because they assumed that somebody was cheating on taxes. Because what they found was that invoices were missing. So you have invoice number 1, you have invoice number 2, you have invoice number 6, you have invoice number 9, you have invoice number 15. Where are the 10 missing millions in between? Because if you're sending invoices, what they want is to have an uninterrupted sequence of numbers, right? So 1, 2, 3, 4, 5, 6, that's what they want. So if there's something missing consistently, they don't like that too much. And if you're a government bureaucrat with a background in bureaucracy, in database, it's very hard to explain to those people that there is a world beyond your desk with real physical people, with labor, productivity, stuff like that. And this is how you produce that. It seriously happened they were trading some medical stuff, right? And they were missing thousands of receipts, right? And this is how they did it. Does anybody see anything obviously wrong here? Apart from database consultants. You see the sequence here? That can kill you. You have a sequence here, you create a sequence, you take the next number, you get 1. You take the next number, you can get 2. But what if you roll back? You start a transaction, you take the next value from the sequence, it's obviously going to be 3, you roll back, and the next number is going to be 4. So this number is never going to be committed into the invoice table, right? So you got gaps in your receipts, just because you got a rollback for whatever reason. And this means you got invoice number 1 to 1 million, but you only get 600,000 real invoices, right? And they're going to see that even the biggest idiot of a tax collector is going to see that. But that's because that's the only thing he was trained on, right? Okay, so that can blow you up. So if anybody is doing finance here, or if anybody is doing accounting, please make sure that you do not use sequences in order to produce your serial numbers for your receipts, because that can blow up in your face. I can show you later how to do that properly. But that's damn serious. And the second thing we had that was really, really harsh. Saturday, 9:30, 10 years ago, I would say, there was a crash at an insurance company, and they lost 1.4 million life insurances, meaning each of them, everything was fucked. They had a backup with a retention time of 2 weeks, but the problem was that the backup was not broken. It was not broken enough to be detected, which means that this thing wrote a megabyte of data to disk, but 5 bytes were wrong, something like that. So it was slightly off, off by 1 byte, or, just slightly broken, but not broken enough to be so broken that you could see like being aborted or something like that. So 1.4 million life insurances, that's the thing you pay for 30 years, right? Boom, including the shit backup, right? So we managed to get this back. I think, were you involved in that one? I'm not sure. Oh, Sultan, I believe. Anyway, so the thing was the aftermath. Their asses, it's Saturday at night, so we fixed that. And then those guys come in. Data protection is a luxury thing. If you're sitting in Stalingrad starving, you don't care if your neighbor knows your phone number. You only care when you're sitting well-fed at home, right? Same with those compliance people. Did you delete the data? Yes, I deleted the data. Can you prove that? No, I was sitting at home alone at night rescuing your bloody data, right? And when I was done, we deleted it. Data has to be deleted according to the 4I principle. Please delete the data. I can't, it's gone. It's not there, right? And even if I wanted to, I could have made 50 copies, right? It took us 6 weeks of paperwork to sort out the shit until somebody in this compliance terrorist organization eventually believed me that the data is really not there. Right? It's very hard to prove non-existence, right? For whatever reason. So that's some of the stuff I wanted to share with you. But at the end of the day, you know, when you do a proper job, you know, you do consultancy, you do programming, you do training, everybody likes, you know, when things are over, to have a little bit of positive response, to have some warm words, to have the feeling of, you know, acceptance. This is what I got. One guy came to me and said, "You're one of the best MySQL consultants we've ever dealt with." Thank you for your attention. Any questions? Any questions, anyway? Yeah, that's us. So if you have any spare CVs, if you have nothing to lose, you know, if you're desperate, just drop me an email. Thank you for your attention and have a nice meeting. So that's my tragic life. So, any questions, or can we go directly to break? Well, everybody wants a break, so coffee. Thank you.
We'll have a break for 50 minutes.
You're the best MySQL consultant.
I know these words. Our dearest, our dearest leader of MySQL. You were not forced to choose one.
You should have just wear phones.
Big contract actually. There are one server, 6 PC. Users and after working hours, kind of machines actually assembling computers there. And here is big manager comes in and he looks around. DTK computers from you. You are selling us Chinese no shit. And the computers came. This is so like this is another word. If you just stick onto the chassis, you know, here it is DTK now.
And they get all themselves.
No, Greeks to to explain to him that this is the DPK motherboard there, and this is there for the DPK. There is a page with the motherboard, but you see, he went to check this to confirm my story before he paid the bill.
You got this thing, information straight away.
They were developing the Salisbury unit transistor, which came in the life in 1993 because first growth for those application was huge deal at that point, 1 gigabyte. But the findings that was the first time the UN implemented something like that. And UPROFOS was the name of the mission, was actually the first large-scale mission. So the findings that start to come out of this data were following. The French people, the army state, the equipment of the United Nations, if it's armored vehicle or regular vehicle, it's I don't know 3 to 5 years. Armored vehicles is like 30 to 25 years for the of them. So they report that the vehicle had stepped onto the mine, and they let off people. Which they show them the vehicle that really stepped on the mine somewhere, but it's in between four lines, you know. So they look through the binocular and they say that's our vehicle. And they write off one vehicle that being chassis number of nothing. Then they call the same guys in the other part of Croatia. They said, okay, we have vehicles to write off, and they report again a vehicle somewhere in the field that really stepped on the mine. They gave the same VIN number. It could be like, you know, Germany army people or some of these subject, the French people they were reporting it's their vehicle. They were fight. So it's got to be and then the things start how the data that should take to the General Assembly field operations meeting that those things have come up. And that enough by bringing the series to the data in New York, and they make the queries and prepare the reports. And the guys that were there, the chief of the operations mission came to them and said, okay, you're crazy boss, which is a British guy, is going to show this to the General Assembly Commission. Do you know that after he shows this, you should actually have protection that goes with you, like bodyguards, because you're going to get killed? I don't know, millions. And they might want to cross it. This is how you
We will see. Push in the right direction. Do we already have time for tomorrow?
No.
I have until Sunday.
We have no enough testing. With the single instance, now chance for the clients to test how the information immediately becomes a production. There is like
This is for you.
no. We really get to go there. Explain that.
But I think all the problems are resolved by
We know we can do it.
They tried to develop it. It would be like it's like all the money. So they will do this take something from back the current because that's production. You don't want to touch that. You want to go somewhere else just to see how was your and they will see something that is going like a story with a bunch of checkboxes and you know and levels. They just start to people not from very far. The person that
It's no real number, and just like 4,
And they, from the beginning, you know, the PM and PS, that's faster than us. And at the beginning of the resolution. Master,
Yeah. So,
one step back. One step back. On behalf of the shareholders, what did you find when you said no? What was it? President of the law, you know, privately employed, you know, Mercedes. Yikes. Even babies in W away from the green.
I just parked outside. Next to my people. For real.
Drive around together. Just pretend. Really touches me. Leave a guest.
Can you cry with
Dear guests.
Can you cry with me?
Yes.
Armin had to buy the Mercedes because his BMW was I mean, how miserable can it be?
Okay.
they people buy proper car.
I can't stay this over.
Okay, so we have the second speaker with a deep dive into the optimizer of PostgreSQL. Please, your applause, Hans Asma.
So, hello everybody. I'm also from Cybertech, and I'm going to be a lot more boring than Hans was, because I'm going to talk about the boring stuff of Postgres Optimizer. So, all of the blah blah. Hans already covered that. So, starting from the beginning, why do we even have an optimizer? So the goal of the Postgres Optimizer is when you write a query into a database, the database has to figure out which order do we want to execute the query in. So in some programming languages, you tell the programming language, do this thing first, then do the second thing, and then a third thing, and then loop. In SQL, you just write, I want this, and you have the database figured out. And the optimizer is the one that is responsible for figuring stuff out. And so how do we do this? And the first part is the database just parses the query, finds out which tables are involved, well, how do we join them together, and what is inside of the query. And from that, we build basically is called a syntax tree or query tree that we then can analyze apply some transformation on it. So we calculate some costs for all of the different operations that are inside of that query tree. And then we try different ways to look up all of that data. So, for example, if we are selecting from one table, we need to figure out do we use an index for this? If there is a multiple where clauses, which index do we want to use? Do we want to use the index in the name or the index in the gender? Or do we want to do a sequential scan? Or maybe use an index on both and join those indexes together. And there is never a correct answer for this that is hard-coded. It always depends on the data and the query. So that's why we have a cost-based optimizer in Postgres that uses some statistics that are collected about the data and the cost model to figure out which one of those options is the best. And then we take all of those different options that we can use to access the data, and we take the cheapest one of those using a trick called dynamic programming, which means that we first take a small part for a single table, which is the fastest way to access a single table. Then we take tables two at a time, which is the fastest way to access two tables joined together, and so on and so forth until we have a plan for the whole query. And we know that this is the cheapest one. So what is cost? It's not dollars in Postgres, but it's a number that signifies approximately how much time it will take. Because we are using statistics, as you all know, there are lies, damn lies, and statistics. The statistics are always wrong, but we at least try to figure out which would be better. And this cost is doesn't matter if you are running on the Raspberry Pi or the fastest server you can get. The costs, at least if you install Postgres by default, will be the same. And that actually doesn't matter because it's only the relative cost of different plans that matters. So there is no unit of time that is associated with the cost. It's just an arbitrary thing. Another thing is, because we are planning every single query, and the query might be a simple one, just look up this one row based on ID. We have to do the estimation extremely cheaply. But we do at least want to do some optimization work, because otherwise the query might take hours to run. So we have to find a balance. How much time do we spend on optimizing, and how much time we spend on execution. So now, how do we calculate those costs? We have different kinds of parameters that give Postgres the information about how much every single move that it does in a query execution takes, how much time should it take. So how much cost do we calculate for that operation? So as sample one would be sequential page cost. And this calculates how much time does it take to read one block sequentially from disk. So if we have a table that is 1 million blocks, we are going to calculate that it will cost $1 million to scan through all of that table. But that's I/O. We also have CPU operations. So every time we do some kind of an operation, we calculate the cost of that operation. Or every time we move a row from one place to another, that's also some cost. So moving data around after we have done the I/O also is considered to cost something. Another cost is random page cost, which is by default 4. And random I/O is usually more expensive than sequential I/O. Random I/O is what we do when we are, for example, scanning an index in the order of people's names. The names will be in alphabetical order, but the data on this will be in an arbitrary order, and every read might go to a different page, and we need to do an I/O into an arbitrary location. But now the situation has changed for random page cost quite a lot. The old times when we had like hard disks made of spinning rust, when we needed to find a different block on the disk, we had to take a mechanical arm, move it to a different place, wait for the platter to spin around, and then we can read it, and then we can do the next one. Now we have flash disks, so it's much faster. But still, random scanning is a bit more costly than sequential scanning, because with sequential scanning we are doing some optimizations that we can read ahead. So with random we have to read one block, get the result back, and only then we can do and read another one. So it's one after another. But with sequential scans we can read multiple blocks at the same time to read ahead. But now at the time that we are planning the query, we actually don't know which blocks will be in the cache and which ones will have to be read from disk. And what Postgres does is completely ignores the problem at all. It doesn't care how much will be cached and how much not, at least at the top level. And it will just calculate some kind of number based on how many pages are accessed. But this also means that when you are adjusting those costs, you should actually encode in that number how much of the data you expect to be cached and how much not. What is typical these days is memory is pretty plentiful compared to data, and a lot of databases can actually cache the whole thing. And in that case, you should take those random page costs and the sequential page cost and bring it way down, like 10 times down, to tell to the database, I don't care about I/O, I care about CPU costs. Optimize that. Optimize for that. Okay. So as we said, CPU is not at all free. We have to execute functions that read a row from the page. We have to execute functions to calculate if the where clause is true or false. We might be doing some complicated transformations to the data, and we might be joining the data together through multiple places. So for that, we have those three parameters, like CPU total cost, which is for moving rows around in the plan, operator cost, which is calculated for the operations that we are doing, and index total cost, which is when we are processing rows in an index. So the best way to see this is using an example. Let's have some sample data. Really simple table here. We have an ID column, name column, then 2 million rows with Hans, 2 million with Paul, and then we need to analyze this. So analysis for creating the statistics that we use for planning the queries. And the statistics are key, are the most important thing to getting good query performance and good query plans. The database does not know what the data is, it cannot figure out the best way to access it. And what the analyst does, it will sample the data. I think by default it's approximately 250 megabytes of data at most. So even if you have a table that is 10 terabytes, you'll only read 250 megabytes of it, and then calculate some statistics on it. And usually it's done by auto vacuum, but sometimes you need to give it a kick, and you can do it manually using the analyze model. So what are the statistics that we are collecting? You can use the PGStats system view to figure that out. In that view, we have first 3 columns are telling us for what those statistics are. So we have the schema name, table name, and the attribute name or column name. And the inherited one just means if it's for a child table or for a top level table. But the important stuff comes after this. First, we have the null fraction, which tells us what percentage of the rows actually contains any data and what percentage is null. Then we have the average width, which is really important, for example, for sorting data. We need to figure out if the data will fit into memory or not. And we can tell this by adding up all of the average sizes of the table of the data. So for an integer, it will be 4, but for text, it will be average length of the text. And then the next one, the n distinct, that's the most important column in here. That tells the database how many different values are there in this column. And if you look at it, it might have values that are positive, something like 1,000. That means there's 1,000 different values that can be in there. Or it can be negative, and then it will be from 0 to -1. And that means what fraction of the rows are unique. So for example, if it's -0.5, it will tell the database that approximately half of the rows are unique, in the sense that if you have 1 million rows, then it will be 500,000 different values in there. And there are the most common values. So what is the most popular thing? If there is like 90% of the tasks in your database are done, the most common values thing will tell the database, okay, this is the most popular thing. And the frequencies is just a fraction of the rows that are that specific value. And let's see, there's some examples here for the ID column where we have the histogram and the correlation shown. So we can see here's the average width is 4, the n distinct is -1, which means that every row is unique. And we also know how big the ID values can be based on the histogram. So the histogram will have as many entries as you have your statistics target, which is by default 100. So there will be a histogram with 100 buckets. Each one of them has the same number of rows. So if we know that the table has 1 million rows, then between 40,000 and 80,000, there will be 10,000. And in this case, we have 4 million rows. So we know that between 40,000 and 80,000, there are 40,000 different rows, approximately. And we can also use this to find some different counts. So, for example, if we look from 60,000 to 130,000, we can take a portion from here, a portion from there, the whole bucket from the middle. And another one is the name column here. See, here we can see the instinct is positive and it's a number 2. Average width is 5. Can anybody guess why it's 5, not 4? So that's because the text columns also have a length prefixed to them. So we have to add a length to our data. And then here you can see the most common values and the corresponding frequencies. And as I said, statistics are always wrong, so it's not exactly 50%, it's slightly different. And correlation is one, which means correlation. We have something about it later, but correlation is how is the data organized in the table? Is it in random order or does it go in increasing order? Unfortunately, that's the two things that it can determine that is it decreasing, or random, and or something approximately in between, but it doesn't know that that if the value that is in the middle of the thing is at the end of the table, it kind of doesn't have any way to describe a more complex layout of the the ordering of the data in physical table versus logical ordering of the values. So let's go through the work that the database does to figure out the cost values. So to see the cost, you use explain, get an explanation about how the database wants to execute your query. Here we have first we set the maximum parallel workers to 0 just to avoid extra complexity. Otherwise, Postgres would do a parallel query on the table. Here we are doing a simple count star from the test table, we're just figuring out how many rows there are. And the plan is very simple. The sequential scan, which means go through the whole table and output all of the rows, and then aggregate them together. And here we have the cost numbers, the cost for executing the sequential scan on the table, and the cost of aggregating it all together, which includes the cost of the sequential scan. So let's figure out how do we end up with the numbers. So if you look at the size of the test table and divide it by the 8K, that is the default page size of Postgres, you see that we have 21,622 blocks. And each one of those will cost 1 unit to scan. Then we will have 4 million rows in there. And each one of those will cost 0.01 to process, which gives us together 60,000. As you can see, we already calculate that the CPU cost of throwing all of those rows around is more than the I/O cost. Yeah? And finally, in the aggregate node, we need to add all of those rows together. Adding rows is an operator, which by default costs 0.0025. We add this together and get the 71,622. And then that's how we end up with those values. So can somebody figure out why the 0.01 here on the aggregate node? That's for outputting the final count. That's the one row that comes out from the count. So yeah, the costs are abstract, but if you want to know what actually happens, then you run explain analyze. What this does is it executes the query that you gave it. So if you are doing an update or delete, be aware that you are actually executing it. So you don't want to run this outside of a transaction. If you need to get an explain analyze plan for an update that is slow, start the transaction, run the explain analyze, and then roll back. But what this analyze does, it then when the query starts, it tells the executor keep track of all of those numbers about how did the execution go. What it does is every time the plan node here, the sequential scan outputs one row, or actually when the sort node here asks from the sequential scan, give me one row, it starts the timer, and when the row comes back, it's the timer, and all of that time gets added up. And that's what we see here in the actual time problem. Here we have two numbers. In case you have a question, what does the first number mean? It means how much time does it take to output the first row. And the second number is how much time in total it takes to output all of the rows that are expected. And both of the time and cost are inclusive. So if you are looking at an explain plan, you want to start from the top and go down and follow the money, so to say, follow where is the majority of the cost coming from. It's completely useless to look at the portion of the plan that doesn't take any time. If something in the query plan is taking 1% of the time, even if you make it 1,000,000 times faster, you will only make your query 1% faster. Some stuff to look for here. Here we have sequential scan. You can see a filter node. And the rows removed by filter. You can see that we have almost all of the data removed by the filter. So that's actually the best tip for optimizing queries. Make the query faster. There are no tuning parameters that make Postgres faster, because there is no evil guy behind the scenes that would just make Postgres slower for no reason. Postgres is already as fast as it can be, but how do you make the query faster is you do less work. And one of these cases is here. Most of the work is removing rows by filtering, and we need to get rid of that to make this query fast. And for the time part, you can see this one and that one are not that different. So that means that the sort itself took very little time. There is no point in optimizing the sort or tuning it somehow. We need to deal with the one that is taking all the time. So how do we do that? Usually indexes. So it's always a missing index, pretty much. From the time you come to a performance issue, your first guess is indexes, and most of the time you're right. So here we are creating an index and ID column. And now when we are selecting rows that are less than 10 in order by ID, you can do an index scan. The index can be used to first look up the rows that are matching this range, and also to provide the ordering. Now the cost is much smaller. If you would have run explain analyze, probably it was happening a lot faster too. Indexes also give us some nice tricks that the planner can do. So a dumb way to execute this minimum ID, maximum ID would be to take every row from the test table and then just execute the minimum function and then the maximum function. But the Postgres optimizer has some transformations built in specifically for minimum and maximum columns, where it knows if it sees those functions, it can actually use an index scan and the limit, which basically means that it finds the first row using the ID index in ascending order for the minimum value, and for the maximum value, we do again an index scan, but we do it backwards. So we start from then, take one row, and voila, we have our maximum. And as you can see, cost is pretty small. So let's see, what about the correlation column in the database? Why do we keep track of how the data is laid out in the table? So we can have a different cost, even if the data is exactly the same. So let's use the same table, but let's make it in a random order. So let's start from test order by random, stick it in the table, and put an index on it, and analyze it. So we have the up-to-date statistics on it. So when we are querying from the sorted table based on ID, we are calculating the cost of 320, and we actually have to access 85 blocks of it. So 3 will happen to be in cache, 82 have to be read from disk, 85 total. But now when we access the random table, the query is exactly the same. First 10,000 rows based on ID. We can use an index scan, but now we are actually using a different scan here. So whereas here we used just an index scan, with the random data, Postgres decides to use a different kind of scan now called the bitmap index scan. If anybody doesn't know what the bitmap index scan does, it actually scans the index first, finds out all of the locations of the rows that are matching the condition, then sorts this location and reads the pages in order, which makes it quicker, especially on spinning Rust disks, but also on flash disks, because you might reference some blocks many times. So you can see the cost is planned. How much is it? 60 times larger, just by rearranging the data. We had to access 8,000 blocks. Actually, only 30 blocks from the index and 8,000 from the table. So the bottom row is for figuring out where the rows are, and the top one is finding those rows. You can see that most of the cost is calculated to be in finding the rows, and also most of the time goes there. It's only 1.9 milliseconds to scan the index, but 45 milliseconds to look up the rows. If you want to fix that, Postgres has a command for that. That should be our tagline. Postgres has a command for that. Cluster helps to reorganize data. So if you have an index in the table, you can use a cluster table name using some index and rearrange the data in that order. But be aware that first take some disk space, because we need to store that table twice for a few moments. And it will forbid anybody from writing to that table, accessing it. So it's not something you want to run on a huge table on production. So if you want to do that, you can save your ass with PG squeeze. You can rewrite the table with less extensive blocking by rebuilding it in the background and then logically replicating all of the changes into it. Now let's see, why are we keeping track of the indistinct? One of the major reasons is we need to figure out how many rows we have to figure out the memory cost, for example. So here we have two different plan types, hash aggregate and proof aggregate. So what hash aggregate does, it just builds in memory a hash table and sticks all of the rows in there, updating the state for each row, which needs, of course, as many entries in the hash table as we have different groups in the group by. Whereas the group aggregate it takes as an input this grouping key. So data sorted by the grouping key, then reads the whole group in one total, updates the state, and then has an output for that. That's why also you can see here the cost for the group aggregate starts from almost 0 because we have the first group ready almost immediately. Whereas with the hash aggregate, we have to scan through all of the data first, and only then we can output what the counts are. And we use the row count to determine if we can fit all of the data in work memory or not. So in this case, we have here the width. That's how much space do we need. In rows, that means that this one would have needed 48 megabytes of data plus some overheads are calculated into it. So you need to bump up work memory somewhere above 40 megabytes, probably double that even. But the overhead is significant compared to narrow like 12 bytes. But for 2 rows, we can easily fit that into the work memory that is the default 4 megabytes. Any questions so far? If not, let's continue with the transformations that we can do. The most important part for Postgres is that it can propagate equality. So if we have, for example, a join condition here that makes 2 ID columns equal, and the different one that says the A column is 15, then behind the covers, Postgres knows that everything that equals is the same value, and it therefore knows that the D ID is also 15. So we can build a plan where it doesn't actually have to do anything major. It can do the index scan on A, using the ID is 15, and B completely independently the same condition. This is very important if we have a more complicated plan, but there are many joins, and the value that is actually specified might be many tables away from the one that where we can use the best index. And what the planner can do is some constant coding. So for example, if we have constant operations here, 14 plus 1, Postgres knows we have a constant value and another constant value, and we have a function that does not depend on the database state. Then we can add those two together before we start the query and use it in the planning phase. And we know that we will look up the value 15. But if we do it slightly differently, so for mathematicians, those two queries are the same query, but for the database, they are not. Over here, we have an ID minus 1. We do not have an ID index, an ID minus 1, so we cannot do anything to look it up more quickly. And therefore, we have to do a sequential scan. So, in theory, the database could figure it out, but as we said, we want to plan the queries quickly, and so we don't want the generic logic theory prover simplifier thing to get rid of crappy queries. We should hope the users to just write good queries. We can also inline functions, which can be really powerful, but we can only inline functions written in SQL. So here we can see we are doing a function that does an base2 algorithm. And if we are using that in a query, here we can see that what Postgres figured out is that this LD of the ID is actually the log function of Q at the ID column. And over here, it figured out that it's a log of the ID column, log of the 1024. But it also then knows that it can execute this log function because it's again immutable. And we know that it doesn't change ever if we have constant parameters. So we can do it before we plan. In this case, it didn't help because the inline function is not indexed. So some queries are also optimized. They can be pulled up into the main query. In this case, I think it's not pulled up, but the main query is just limit because it's the only thing in here. Limit usually doesn't allow for pull up. But in other cases where you have joins and other things, then it can actually figure that out, that everything can be joined in one step and done in different orders. So for this query, you can see that we have select star from and select star from, but the plan looks just like this inner query, just an index scan and the limit. Views are also inline. And actually, the better way to specify that they are replaced completely. So they are basically written in the query as a sub query. So if you have a create view B as select star from test, and we do a select star from B modeled by ID, then what happens internally is first Postgres during the parsing phase takes this V view, knows, okay, I found a view here. I will look up the view definition and then we'll replace this V here with the query tree from that view, like a subfolder. But then the optimizations that we discussed earlier that can get rid of our subqueries, and then analyze that, okay, we have two order by IDs, we can skip. We can merge them together because we don't need to reorder anything and we can just use an index scan. Okay. That also means that if the view contains something like limit, you cannot get rid of a limit that easily, and you have to be more careful with that. So, join pruning. So we can get rid of some joins that are not affecting the query output. Adding a couple of indexes here. So the planner has more information available to it. But over here we can see that the output or the plan can depend on what the select list is. So the select star is not always the best idea. It's almost never the best idea. You should ask for the data you actually need. But in this case, let's assume that this inner query is coming from a view and we cannot get rid of that join easily. We're just rewriting the query. Then Postgres can figure out on its own that in this case, if we are selecting star, we actually have to perform this join to answer this query. Whereas if we don't care about the B values, we don't actually have to perform that join because we know that there can be only one row from here or 0 rows. But if it's 0 rows, it's going to be null. And we don't care about the difference if it's null or some value. So we can actually skip the B table all together. We don't have to do a join or anything. So join order matters, and it matters a lot. That's actually the most important stuff when optimizing a larger query, figuring out what is the best join order. So the goal would be to get rid of as much data as possible. So instead of joining 1 million rows and 1 million rows and then filtering all of them out a bit later, we should first try to do the filtering and then join to the other stuff. The Postgres does that automatically by trying all of the different join orders, but only up to a point. And so in Postgres, there's a config parameter called join collapse limit, which will tell the optimizer only consider this many tables at once. By default, it's 7. So if you have, let's say, 8 tables, and the best join condition is on the, or best filtering thing is on the 8th column or the 8th table, Postgres will first join the 7 tables, and then maybe get a huge result set, and then join together with the 8th one and narrow it down, which will be very slow. But if it's slow, why do we do that in this way? Why do we even have that config parameter? And the answer is that calculating all of the join orders is surprisingly difficult. So it's basically not even exponential, but even harder than exponential complexity. So with something like 7 tables, we might have to consider hundreds of thousands of different join orders to do stuff in. That would make the planning extremely slow if we try to do that for like 20 tables. So that's why we have a join collapse in there. And not all joins can actually be reordered. If you have a left join, we first have to do the first part, and then we can do the right-hand side, and vice versa for right join. Because we cannot do it in the second order, because for the left-hand side there might not be any rows on the right-hand side. Actually, Postgres optimizer can even figure out if you have a foreign key, then I think it can convert the left join into an inner join automatically. It knows that there always will be a row. And finally, I think I blew through this much too quickly, but there's still a lot more to go through. So this is just an introduction. I didn't tell you anything about how parallel queries are planned or handled. We have also like unions and intersections. We can do great statistics to figure out cross-column correlations. There is selectivity calculations that may matter. We have the effective cache size, which is, I think, the most misunderstood parameter in Postgres. People are always trying to figure out what is the best way to tune this. Actually, it doesn't really matter that much, because it's only about figuring out how many cache misses an index can has. But also in statements, which either if they are a list, and the one way they are a select, they might be converted to a join. There is exists, which is a special type of join. There are different index types. You can some indexes can output sorted rows, some cannot. We also have plan caching, so all of this work can actually be saved and reused if you use prepared statements. But Postgres is actually smart and figures out, do we want to do the same thing every time, or if using the exact values that the user has specified is actually important for planning the query correctly. So in some cases, if you are doing something look up by ID, there is no other way to do it reasonably. But in other cases, the specific values that are specified are important in selecting the correct plan. Postgres tries to figure that one out. But that's it so far. Any questions?
One question. There was in the slides that you can control if you will be in line or not. Is there any? How is control?
Actually, that's a good question. That was also my question. Those slides are not my slides. It's Hans-Jürgen. So maybe I'll delegate that answer to him. Because I don't know way, but there are so many config parameters in Postgres that I might have missed when it got added.
There's the form collapsing. The form collapsing basically says how many subqueries you're gonna pull out. So the join collapsing it says how many implicit, how many explicit joins are done implicitly, and the form collapsing it says how many subqueries can you pull out, because that's exactly what's happening in the queue. And the next option is to just to leave it null in the queue, because if the optimizer sees a limit, it doesn't dare to optimize it, so it doesn't pull it up. If you just do offset 0 or leave it null, then it doesn't pull it up. But it's
Okay.
not necessarily a parameter, that's just very difficult.
Okay, yeah, from collapse limit is indeed, as I discussed, that view is basically written in as a subquery, and if you don't pull up subqueries, you don't pull up views.
I have a question.
Sure, hit me.
You should know.
It's another one. Can we have optimizer hints?
Not in core, not in core, but there is actually an extension for that. PG hint plans. Supposedly it works. I haven't tried it in anger yet, but supposedly you can tell the optimizer that if it's trying to do something completely stupid, you can kick it in the right direction, and it actually has the useful ways. So usually telling the optimizer do exactly this is not a great idea, because 1 year from now the data will be different, and then your decision will be bad. But if you can figure out that this is where the optimizer is going off the rails and deciding that there are like 10 rows, realities there is 10,000 rows, then you can kick it only to figure out that, okay, this join will output 1,000 times more rows than you think it will. And usually Postgres will then figure everything out. And it's actually simpler to, if you find the place where it goes off the rails, just help it back on track, and then it's better than telling it exactly what to do.
Custom plan. There's an API where you can push in your own extension and reprocess the plan.
That would, yes. If you are insane, you can do that also. But if you are insane, you could try that. But that you use the PG hint plans that outputs, that gives you a nice API to do that, the same thing from SQL.
We have parallelization, and is any rule or general rules if optimizer decide to use parallelization or not?
Well, the main costs of parallelization is spinning up the helpers, which is calculated to cost 1,000 units. So if your query is simple, you will not use parallelization. And the other main cost is costs significantly more to pump rows between the parallel worker and the main query that is executing it. So if you can make sure that the work does not have to be collected, so it's actually reduced in size before being collected together, that's helpful. So I don't have any generic advice about how to achieve that. It's really case dependent. But Postgres actually does know how to do that. So if you are aggregating together, it can do the aggregation in 2 steps. So first, every parallel worker does aggregation, which reduces the amount of rows, and then we pump it up. and we add them together one more time.
That's because sometimes the same query use parallelization or not.
Probably it's this plan swapping is pretty common when the costs happen to be in the same level. So because it's using statistics and statistics are always wrong, it may happen that it decides to do one or the other, or it may actually happen that it's correct, that it doesn't really matter that much either way. But usually if it's swapping between one or the other, it doesn't get it that correct that it's like exactly the same performance.
And also in some moments it's because of size of the data set.
Yeah, data changes, parameters change. But there is no random in the query planner, so as long as nobody runs analyze or auto vacuum runs analyze, then the same query should get the same answer.
Are there any projects that try to use artificial intelligence to apply optimization?
I think I saw a paper about that some time ago, but I don't know of any real databases that do this.
I'm not sure that it's about artificial intelligence, but I remember we have talk with a guy from Japan. They try to use.
Oh yeah. Yeah, I think that what they did, they collected statistics about how the execution really went, and then put that back in the optimizer. So the optimizer calculates the initial statistics based on what analyze collected. But then when we execute this query, we know that actually it went completely the other way. This join, we expected to filter everything out, but actually it happens that everything had a match and we had 1,000 times more rows. Then this extension collects this information, gives it back to the optimizer, and the optimizer really knows how to pick a different plan next time. But there is no artificial intelligence, there is just good old human intelligence that programmed this.
What we need is optimizer for optimizer.
What we would first need is some kind of abstraction that knows about the queries more than in a single connection and a prepared statement, so we can keep track of what queries there are and cache this on the Postgres level. Currently, when I discussed this plan caching is only in a single connection for a prepared statement, or within PGDay functions. There is also a plan cache. But you cannot share those plans between different connections. I think once we get the opportunity to share those plans, we can do lots of smart stuff like spending more time optimizing it. But we could also share things like the just-in-time compiled executor functions. So we can do cheating of queries and share that even for small queries. So that's all. No more questions. That's all from me.
And today we will have one more session from Pavlo.
Oh, I didn't know. Okay.
Yes, a moment.
So it will be the excerpt of the talk, starting with the Cold War topic. How many administrators here and how many developers? Wait, DBAs. Okay, developers. Okay, let's go. So, that's supposed to be me. Okay, so we are. Yeah, now we are. Okay, no.
Okay.
Questions?
Okay, so in some case, when it all goes right, it's supposed to tell you about how to interact with PostgreSQL from Go language, because Go language is now the 10th top post just by TOB index. So I have, yeah. So and there was a survey among the Go developers, and 68% said that they are doing web programming, and 46% said that they are doing databases. So if you are doing web programming with databases, you are 100 plus. So that's why I decided to make this talk. Okay, and blah blah blah. Okay, these tools, whatever we have, and drivers. So drivers are the packages which we are using to speak to the PostgreSQL server. And I must say that many people say that ORM are pure evil. Yes.
Except Gorm.
Except Gorm. I would say Gorm is unnecessary evil. Why I'm thinking this way? Because ORM gives you nothing compared to the SQL itself. You must learn how to do things in ORM, but why do you need this if you know SQL? The only reason when you need it, if you want to easily serialize, deserialize objects and relations, but that can be done with simple packages, and I will show you what are they. So the fundamental way of working in Go language is with databases is a database SQL package. In fact, it's a package consisted of interfaces only. There is no any implementation. But for any database, file-based or whatever, you know there are some methods you should call to get the results. And to use this, you need some kind of implementation package. So if you are using database SQL package, you need one of the two for PostgreSQL packages. The old one called libpq, and the modern one called JAX-PGX. I mean, JAX-C is the author, of course. PGX. How are they compared? And when you should start with the libpq, or when you should start with the new PGX? If you are starting the new project, go with PGX. It's fine, absolutely. You can use it with the database SQL through the special standard lib library. If you are stuck with the old one, project, or if you are using several databases, just like MySQL or Oracle or whatever, and you need to work with them simultaneously, then probably you want to go with a standard library. And if you're using GORM, then you should also use the standard library, because ORM packages have no idea how to use this special PGX, because PGX was created specifically for PostgreSQL. It has native support for every base data type. It has automatic preparation and caching for statements. It can do batch queries. Send them at once, not just round trip between server and client. TLS, binary format, but the most useful thing is the copy protocol. You cannot do copy protocol if you're using standard library. It just doesn't fit. There is no such methods. Remember, the base skill is just the interface. There is no method for copy. And login support, pooling, Listen.fy, by the way, you cannot implement listen.fy in the standard library. Some fancy conversion from each store, JSON, JSONB, large objects, etc., etc. Okay, so how we do it in the old-fashioned database SQL? We declare database SQL package in the import section. Remember, this is just interface. Now we need implementation. What we do? We use PGX. We say v4, it's the v4 version. And we say use standard lib. We say, please PGX import standard lib to understand these interfaces and to work just like we are all people. And then we do it just like in old days. We call open, we check errors, we defer closing, we querying, we check in errors. By the way, in Go language, you are checking errors every time. You cannot ignore the result of the error. Oh, I mean, you can, but I will fire you. And linter is telling you ignore the error. But the idea behind the database SQL is that DB is not a real connection. It's a pool of connections. So every time database SQL thinks that you need a new connection, for example, if you parallelize something in Go routines, it will create a new one. And if you have a limitation on parallel connections, you can hit the maximum connections easily. And you will just like wait for it forever. On the other hand, how the PGX works. PGX says, this is the real connection, the only one. We will do pretty much the same. We will connect, we will check for errors, we will defer the closing. I mean, at the end of the routine, we will release our connection, and we will do pretty much the same. We will query, check, and whatever. But this is only one connection. You cannot parallelize it. You cannot run multiple Go routines accessing the same connection. Well, probably you can, but this would be catastrophic. But what if we need some pooling? We used to it. Okay, this is Go way to use pooling. That PGX provides you with PGX pool package, which is absolutely the same as database SQL, but it works natively with the PGX implementation. So PGX pool connect, and bam, we have DB pool. And then, for example, if here I will run several Go routines asking for some information, they may create several connections, ask for results, and return. And I just don't care how this works. Okay, useful extensions. When I said that ORM doesn't provide you any significant usefulness, I mean that usually people are trying to be lazy and dumb. They want to okay, I have a relation, I have an object, let's magically do things that from database, I will put them into my objects, work, and then magically they will go to database. If you want that, for database SQL standard library, you can use JMoiron. It's also the author. SQLX extension. It extends the standard library with some useful functions and add these new semantics. So you can go get and put the whole relation into the object or to the slice of objects. Yes, exactly. So, for example, we have a place which is structured And just like we have a table called place, and we have country, we have city, which can be null, and we have some telephone code. Okay. So and we are using SQLX. So we just say row up. Okay. We can do it one by one. So we query X, return row. Then we go for each row and put immediately our row into this structure. No need to go one by one field, checking now, whatever. We just put it into the structure. But we can do it even simpler. We can define the structure itself. We can define a slice of structures, and then we can just get one structure. If we have one row, we can put the slice of structures. If we have several, that works smoothly for the standard types. We just can select count, integer, guess. Or we want just slice of strings, we can do that. Pretty cool, yeah? And what about PGX? For PGX, there is the same, not the same, I mean, similar package, which do pretty much the same, but in different way. So here we have, we declared users as a slice of user structure, and we call PGX scan, just select, please, the result from our query to the slide of users, and then you can work with this slice of structures in how you like. Okay. Do you want more? I don't know. I don't know. Okay, so I think that every application must be tested. It's up to you how you do it. You may run some manual testings, or you want to have some automatic testing. So if you have a real PostgreSQL server, you are probably fine, but you can automate it really. Because on every platform you want to run a test, you need to set up the same PostgreSQL version, to apply the same initial schema, to provide the same initial data, and to run your tests. There are two more unit testing approaches, and one of them is the mocking libraries, which are in fact mock the PostgreSQL on the other side. So your application thinks that it speaks to the PostgreSQL, but in fact, there is no PostgreSQL. There is mocking library, and you tell this mocking library what to do and how to respond, and you can test all possible ways of your code. The more complicated way to test is to mock the native PostgreSQL wire protocol. Just like to know, we really create a connection, we really speak to some server, and it definitely speaks to us in the PostgreSQL dialect. Why do you need this? I don't know. For example, if you wanted to check code, how it will behave if the connection is broken, or some garbage is inside the message messages, or what if, I don't know, connection drops and then recreates, and without proper I don't know, TLS things. So there are two ways. The simplest one is the cockroach Go test server. As you know, probably the CockroachDB uses the PostgreSQL wire protocol, and they created this test server package just for testing purpose. So the idea is simple. The first time the unit tests are running, the test server is one binary is downloaded and cached. And later, if you run your test over and over again, the cached version of this test server is used. And the PG mock library is the library by the author of the PGX. He uses it a lot in the testing of these messaging things. So let's see how we can use. By the way, I forgot. I am the author of the PGX mock library. That's great. Okay, so initially I was using Go SQL mock, it's cool thing, and in one of our products I was stuck to the database SQL, and I cannot switch to the PGX because a lot of tests were written for Go SQL mock. So then I decided that world needs a hero, and I created the same sheet for PGX. Simple. So let's see how it works. This is our request start function that we wanted to test. First of all, I will pass to this function not the connection itself, not the pool itself, but I will pass the interface, which will know how to open connection, start transaction, and close it. My function doesn't need to know anymore. You just use the start transaction and commit rollback. That's all. Then I have some logic. Okay, so logic is this: update products with some data. If something is wrong, then roll back. If everything okay, then commit. The trick here is we use that we use deferred function, meaning that deferred function will be executed at the end of the function. It looks like weird for those who are not familiar to Go, but it means use this function at the end. And why so if any of these two statements return error, then we can do the same actions for the same calls. We don't need to check twice. We need to check something once. Okay, and then I want to test this function. First of all, we all like to test the successful cases. So we are creating PGX mock connection, and it returns the interface, which is similar to the PGX mocks. So my function, which accepts the interface, doesn't know that this is not the real connection, not the real pooler. My function knows that he can use begin transaction method and the close, rollback or commit. Then I need to tell my mocking library, mocking object, what I'm expecting from my function. So I'm saying, so my function should start transaction and say, I expect begin. Then I say, I expect execution of the query. And here I just use the first words, but in reality, you can use complicated regular expression, for example, or callback to check if this is the right. And then I say, I expect that this execution will return result. What kind of result? It will be okay. It will be update result. One row will be updated. Okay. Then I say, I expect that the second statement insert with the arguments 2 and 3 will return good result, and then will be inserted just only one row. And if this everything is fine. I expect that my function will commit this. Okay, okay. Then I call my function with my mocking object. And I pass in 2 and 3 as arguments. And if my function produces error, test failed, because I expect commit, I expect success. Then one more detail. Sometimes your functions, target functions, may do more than you're expecting. So, okay, it will commit, and for example, then it will open one more transaction and will write something else. That's not good. That I can use expectations were met. Only these expectations that I list here, no more nor less. Okay? And the same goes for the failures. But here I'm saying I expect the beginning of transactions, but then when I'm expecting updating of products, please return. Return. Okay. No error. But when I'm expecting insert with the same arguments, please return error. So my function will receive from my mocking connection object error saying that insert is failed. And how should it proceed? It should roll back. Okay. Now I'm calling my target function. I'm passing my mocking object arguments. And if error is nil, that something goes wrong. I'm expecting an error. I said produce an error. And the same here. Expectations were met. Everything gone in the same order, no more, no less. Takeaways. Oh shit. Golang is a popular facility in number most by heart. Kubernetes written in Go. Go is flexible. You can use standard library. You should use PGX. Remember that. And we have a powerful integration. For example, GitHub and GitLab. We can for some of our projects we check security. We check unit tests. We check coverage. And everything, this shit is applied to the pull request. And if you are a developer, you will never succeed. And the most important part for me is that Go is backward compatible. Everything written for the first version of Go is still in place. And whatever they will add later, it will never, ever break the first Go release. Thank you very much. Questions? Yes. Sorry? Go back a couple of slides. Yes. More? Oh. No, not mine, but okay. Yes, and it's not 100 covered. Yes, and I can show using my finger which line isn't covered. And yes, that's done for the purpose of talk. I cannot.
So that's just one question.
Yeah.
Created a database for your products.
Okay.
But you have only one product. Because your update state makes sense to use for all the products.
No, the situation here is different.
You forgot the backlog. the product that you equals to
Ah, okay.
Maybe you
We
have
don't want business logic.
That's, Go developer don't look at this file statements. It's
No,
not important.
never. Okay, yeah, that makes sense.
That's where close business logic in the database.
We all know that. Yeah,
And if you have only one product, you should have all the table products.
yeah. As I told, this is not my code. Well, really, this code was initially taken from the SQL mod library. But yes, I should notice this. No excuses. Yes, I agree. Sorry.
Sorry, what was it?
Sorry.
Did the test library catch it?
No. Because this query is okay, it will work.
It will work well, but all the products.
Probably the best way to catch this case would be to have a real server with the initial data and the data after the modification and compare it. Yeah, that's probably the only one possible way to test, just like.
Or maybe just check with the updates.
Yeah. Or maybe we should have a linter who checks SQL statements and produce errors if there is update statements without where clause.
Or
That's
it
possible.
will produce just the result count so that you can check if how many updates or inserts you expect to be there, and if the number is different, then
Maybe.
drives the error.
Maybe. I mean, I have no idea what this function should do. Maybe this is a correct header. It's just record starts. What that means. But yes, this is a bad. Never ever do update statement and delete statements.
Especially because it's production.
Yes.
This is a database with 5 products inside, and whenever a customer looks, it looks all 5. So you always want to put
Yes.
5 plus 1.
Exactly. Or 6 rows.
Yeah.
We're talking about that guy with yes. Okay. Any other question? Yes, please.
If it's too slow, you will change it to Rust.
I don't think it's slow. I know that the PGX author has a comparison table on his repository. There he has the comparison data for database SQL with libpq, database SQL with the standard lib for PGX, this intermediate package, for the pure PGX connection, and for the PGX pool. So you can see what changes depends on logic and workload. I don't think he has some statistic for C or Rust or whatever, but I think they are quite similar because the Go uses the same wire protocol on the same level as the C program. What can go wrong? Unless you do not specify where clause in that case.
In that case, it's not the Go code.
Okay, if you are yes, please.
What we're saying about the concept presented by Hans, that the logic should be
Depends. It should. Yes, it shouldn't, but we live in the real world, and I saw when it is. So And I saw just like, get clients version 2, get clients version 3, 15 different functions or something like that.
It's okay as long as it doesn't go to bed.
That's true. But I mean, what the business logic? I mean, application logic, business logic. Check constraints are logical, so but you must put it because you want consistency of your data.
Data logic.
But okay, if you are talking about the constraints, but when we're speaking about exclusion constraints, that's some kind of business logic already, because only business know that you cannot book 2 hotel rooms at the same time. But the database, just like, okay, live together. Thanks a lot.
Okay.